Wherever there is water on Earth, there is life. And water exists in more places than just Earth in our solar system. It also exists here, and NASA believes this may very well be the place where humanity first discovers extraterrestrial life. In this episode, we'll talk about why this world might be the one, Europa, Jupiter's moon. If you've been following us for a while, you might have a question. If the presence of liquid water suggests the possibility of life, isn't Enceladus, Saturn's moon, actually more promising? After all, the evidence for water on Europa is mostly indirect. Scientists have built a strong case that it harbors a subsurface ocean beneath its icy crust, but we still can't be 100% certain. Enceladus, on the other hand, is a different story. Its water isn't just hidden underground, it's actively erupting into space. Human spacecraft have observed this from afar with their own eyes. They've detected the geyser-like plumes shooting out from the moon's surface, and they've analyzed these plumes and found something remarkable: salt. What does this suggest? Earth's oceans also contain salt. So the presence of salts in Enceladus's plumes is strong evidence that a vast, subsurface, salty ocean exists beneath its icy crust. That's as close to confirmation as we've ever come. So, here's the question. If Enceladus seems more promising for life, why is NASA choosing Europa instead? This is where Jupiter comes into play. Orbiting around Jupiter comes with a serious hazard: its radiation belt. In December 1973, the Pioneer 10 spacecraft flew past Jupiter. During the flyby, the intense radiation caused the spacecraft to malfunction. Some commands were scrambled, and part of its photo data was lost. While NASA had taken radiation into account, Jupiter's radiation turned out to be 10 times stronger than what the spacecraft was designed to handle. The environment around Jupiter is, quite literally, a kind of hell. And the culprit behind this radiation nightmare? Jupiter's magnetic field, the strongest in the entire solar system. Actually, the magnetic field by itself wouldn't be such a problem. A magnetic field alone isn't particularly harmful to life or to spacecraft. But one of Jupiter's moons gives that magnetic field a serious power-up: Io, Jupiter's innermost large moon. Io is the most volcanically active body in the entire solar system. Every second, and yes, literally every second, it erupts into space with about 1,000 kilograms, 1 ton, of sulfur dioxide gas. This constant volcanic activity creates a torus, or a ring-shaped cloud, of sulfur dioxide along Io's orbit. Now, sulfur dioxide by itself wouldn't be a huge concern. In the vacuum of space, it poses little direct threat to spacecraft or neighboring moons. But here's where it gets dangerous. Jupiter's magnetic field is not only incredibly strong but also enormous in scale. As a result, it ionizes the sulfur dioxide into sulfur ions and oxygen ions. That once harmless gas torus becomes a massive plasma ring. Driven by Jupiter's magnetic field, this plasma spins rapidly, creating a ferocious radiation belt packed with energetic particles: negatively charged electrons and positively charged hydrogen, oxygen, and sulfur ions. The hydrogen comes from Jupiter's own atmosphere. But the primary source of all this intense radiation? Still Io through its constant volcanic activity. Now here's the kicker. Europa, our main candidate for alien life, is located right inside this radiation belt. I know what you might be thinking. If radiation is so deadly, then isn't Europa doomed? Wouldn't any life on or near its surface be obliterated? And yes, that's absolutely true for the surface. Europa's surface is extremely hostile to life as we know it. The daily radiation dose there is about 1,800 times what Earth's surface receives in an entire year. That would be fatal to any known organism. But as with many things in science, there's a flip side. Radiation can destroy life, but it can also sustain it. While Europa's surface is bombarded relentlessly, its subsurface may tell a different story. On March 4, 1979, Voyager 1 captured a photograph of Europa from 2 million kilometers away. At first glance, it might not seem particularly unusual, but when compared with other moons in the solar system, one thing stands out. Europa is incredibly smooth. There are almost no impact craters visible. What does that tell us? That Europa is geologically very active. The only way to erase craters is through constant resurfacing, meaning the crust is being renewed over and over again. When we look at the surface of the moon, we see that it's full of craters, which clearly indicates that the moon's geology is not very active. In contrast, when we observe a celestial body that shows almost no craters, there's usually only one reasonable explanation. Its surface is covered by an ice shell. Over time, water from beneath the surface has risen to fill in the original pits and depressions, freezing into solid ice and smoothing out the terrain. This is exactly what we observe on Europa, one of Jupiter's moons. The absence of impact craters suggests that Europa likely has a subsurface ocean of liquid water. If such an ocean exists beneath the icy crust, it raises the intriguing possibility that life could exist there. The thick layer of ice would act as a natural shield, protecting any potential life from Jupiter's intense radiation. At this stage, however, it's still difficult to say whether Europa is truly more promising than Saturn's moon Enceladus in the search for extraterrestrial life. Europa, after all, is constantly exposed to strong radiation from Jupiter, which could pose a threat to life at or near the surface. But let's not jump to conclusions just yet. NASA has made several important discoveries about Europa that shed new light on its potential. In December 1995, the Galileo spacecraft entered the Jupiter system and began a 7-year mission to orbit and study Jupiter's moons. During its exploration, Galileo made 3 particularly noteworthy observations about Europa. First, it detected a faint magnetic field around the moon. This suggests that there is electrically conductive material beneath Europa's surface, most likely a vast ocean of liquid water lying just a few kilometers under the ice. The interaction between this conductive ocean and Jupiter's magnetic field generates an induced magnetic field, which Galileo was able to measure. Second, Europa is tidally locked to Jupiter, meaning the same side always faces the planet. However, it's not perfectly locked. Europa rotates slightly faster than its orbital period. This imperfect locking indicates that the moon's mass is not evenly distributed. Its outer shell is heavier, while the core is lighter, meaning the center of mass does not coincide with its geometric center. This uneven distribution supports the idea that a liquid ocean separates the icy crust from the rocky interior. Third, Europa's orbit is slightly eccentric and is continually disturbed by the gravitational pull of Jupiter's other large moons. As Europa is stretched and squeezed over time by these tidal forces, friction occurs within its interior, generating heat. This process could help maintain the subsurface ocean in a liquid state despite the moon's distance from the sun. Together, these findings make Europa one of the most promising candidates in our solar system for hosting alien life, hidden beneath its cold, icy shell. One of the key indicators that tidal forces may be generating enough heat to melt Europa's ice layer is the presence of long, deep cracks on its surface. These fractures are strong evidence of tidal stretching. Europa is the only moon in the Jupiter system known to undergo this kind of deformation, and it's this unique geophysical activity that likely creates such prominent surface features. Another fascinating observation lies in the reddish-brown substances found across Europa's surface. Scientists believe these materials were ejected from beneath the icy crust. After analyzing their composition, researchers discovered that they may contain hydrocarbons and water. Spectroscopic studies also revealed the likely presence of sodium chloride, ordinary table salt. This finding further supports the theory that Europa hides a liquid ocean beneath its surface, rich in minerals and possibly similar to Earth's oceans in composition. At this point, some people may still feel underwhelmed. After all this explanation, it might seem like the only takeaway is that Europa has a subsurface ocean, which, on its own, doesn't sound that extraordinary. It doesn't appear to be that different from Enceladus, Saturn's icy moon, which also has a hidden ocean and even visible geysers. But let's not jump to conclusions too quickly. In our earlier discussions, we talked about how the discovery of hydrothermal vents on the ocean floor of Enceladus could provide energy sources for life, much like those deep-sea ecosystems on Earth that thrive without sunlight. In those cases, even without solar energy, life could exist around the vents. However, if Enceladus turns out not to have such hydrothermal activity beneath its icy crust, the chances of life there would be slim. Europa, on the other hand, offers an additional possibility. Unlike Enceladus, Europa is bathed in Jupiter's intense radiation belt. While that radiation is hazardous on the surface, it plays an interesting role when it comes to the moon's potential habitability. It interacts with the thin, tenuous atmosphere, or more accurately, the exosphere, surrounding Europa. An exosphere is not a stable atmosphere like Earth's, but rather a sparse cloud of molecules that continuously escape into space. This exosphere is primarily composed of water and trace amounts of water vapor. When Jupiter's radiation bombards Europa, it breaks apart the water vapor into hydrogen and oxygen. Because hydrogen is much lighter than oxygen, it escapes into space more easily. As a result, the remaining atmosphere becomes dominated by oxygen. This constant release of hydrogen and accumulation of oxygen is yet another sign that Europa is geologically and chemically active. These surface and atmospheric processes provide indirect but compelling evidence of ongoing internal activity, reinforcing the idea that Europa's ocean might not only be liquid, but also dynamic and potentially life-supporting. Now, suppose there's a scenario where the oxygen generated on Europa's surface gets absorbed into the ice and even seeps through the cracks down into the subsurface ocean. If that's the case, this oxygen could become a crucial factor for sustaining life. While this idea might sound a bit bold, it's a hypothesis that gives Europa an edge in the search for life when compared to Enceladus. In contrast to Enceladus's relatively straightforward profile, Europa offers a more complex, multivariable equation, with more possible answers, and thus, greater potential. However, not all the news is encouraging. In March 2024, some astronomers reported that the amount of oxygen on Europa's surface might be far lower than previously estimated. But there's optimism too. Back in December 2013, Galileo detected clay-like minerals on Europa's surface, materials that may have resulted from impacts with asteroids or comets. Some imaginative scientists have even proposed that microbes from Earth could have been flung into space during asteroid collisions and eventually made their way to Jupiter's system, possibly reaching Europa. Regardless of the origin of these materials, Europa is now widely regarded by the scientific community as one of the most promising places in our solar system to search for extraterrestrial life. It has a subsurface ocean, it has the dynamic interface between ice and liquid water, it contains salts, and it has internal heat sources. These factors combined are rare in the solar system, which is why Europa has become the focus of major space missions. On October 14, 2024, NASA's Europa Clipper mission is scheduled to launch aboard a Falcon Heavy rocket. The spacecraft will perform a gravity assist maneuver with Mars on March 1, 2025, to pick up speed and slingshot itself away from the Sun. Then, on December 3, 2026, it will use Earth's gravity for a second boost, ultimately aiming to enter Jupiter's orbit in April 2030. The journey will take 5.5 years. Once it arrives, the Europa Clipper will begin orbiting and studying Jupiter, with its primary focus being Europa, as you might expect from a spacecraft named after the Moon itself, not the planet. The naming reflects not just the mission's goal, but also its orbital strategy. Due to Jupiter's intense radiation belts, which can damage equipment and disrupt communication with Earth, the Clipper's flight path has been specially designed to minimize exposure. Rather than staying close to Jupiter, the spacecraft will approach Europa briefly to conduct observations, then quickly pull away to transmit data and avoid prolonged radiation exposure. This flyby approach, dive in, gather data, then retreat, is not wasteful. In fact, transmitting the data back to Earth takes much longer than collecting it. If the data can't be sent back safely, it's essentially useless. Beyond orbital planning, the spacecraft itself must be engineered with high radiation resistance. After all, it's a robotic probe operating in one of the harshest environments in the solar system. Once a spacecraft is launched into space, there is no possibility of repair. If any component fails, the entire mission could come to an end. For that reason, every piece of equipment designed to go into space must be of exceptionally high quality. Only the most reliable technologies, refined through rigorous testing, are accepted in the aerospace industry, each one representing the pinnacle of high-end manufacturing. One notable example is the red-colored area on the Europa Clipper spacecraft, which serves as its radiation shield. This protective casing is made from 9.2 mm thick aluminum zinc alloy panels and houses the spacecraft's most vital components, such as its onboard computers and flight control systems. The primary goals of the Europa Clipper mission can be broadly understood in 3 categories. The first is to investigate Europa's ice shell and confirm whether a liquid ocean exists beneath it. Scientists are especially interested in studying how substances might be exchanged between the surface and the ocean through fractures or vents in the ice. The second goal is to analyze the surface composition of Europa, exploring what chemical compounds are present and how they relate to what might be found in the subsurface ocean. This connection may hold critical clues about the moon's potential habitability. The third objective focuses on geological exploration. Researchers aim to better understand Europa's surface features, how they formed, and where current geological activity is taking place, especially in regions that may still be active today. To accomplish these tasks, the Europa Clipper is equipped with a variety of sophisticated scientific instruments. Its imaging systems are divided into two main categories. One set includes visible light and infrared cameras. The visible light camera system, known as EIS, Europa Imaging System, includes both wide-angle and narrow-angle lenses. These will capture high-resolution images of Europa's surface, help create 3D models using stereo imaging, and measure surface elevation. The images will also serve as visual references for other instruments. The infrared camera, ETHEMIS, has the specific role of measuring temperatures across the surface of Europa. By detecting relatively warmer areas, it may help locate sites where liquid water could be erupting from below, thus identifying promising regions for further scientific investigation. The second category includes a suite of spectrometers designed to study light in various wavelengths to determine the composition of Europa's surface and thin atmosphere. One of these is the Europa UVS, an ultraviolet spectrometer that will examine the moon's tenuous exosphere, analyze surface materials, and search for water vapor plumes, possible evidence of subsurface activity. Another key instrument is MICE, the Mapping Imaging Spectrometer for Europa. It will create detailed maps showing the distribution of ice, salts, organic molecules, and thermal hotspots. These maps will provide crucial insights into Europa's geological history and help scientists assess whether conditions in the subsurface ocean might support life. The Europa Clipper is also equipped with instruments for detecting plasma and magnetic fields. One of these is the ECM magnetometer, which will help determine whether a subsurface ocean truly exists on Europa. By measuring magnetic fields, the instrument can provide insights not only into the presence of this ocean, but also its depth and salinity. Additionally, ECM can estimate the thickness of the ice shell and analyze how Europa's atmosphere becomes ionized. Another essential tool is PIMS, the plasma instrument for magnetic sounding. This device features 4 Faraday cups and is used to study the density, temperature, and velocity of the surrounding plasma. Plasma in Jupiter's magnetosphere interacts with Europa's atmosphere, breaking down atmospheric molecules and influencing the magnetic environment around the moon. To accurately measure Europa's magnetic field, it's necessary to factor out the impact of plasma interference. PIMS allows scientists to model the behavior of plasma and subtract its influence from the magnetometer data, leading to clearer magnetic readings. The mission also includes radar and gravity measuring instruments. The radio science system uses radio waves to measure gravitational variations as the spacecraft flies past Europa. These variations reveal how much Europa stretches under gravitational forces, helping researchers better understand the moon's internal structure. Meanwhile, radar instruments will directly probe the thickness of the ice shell, assess surface elevations, and search for evidence of plume eruptions. For chemical analysis, remote sensing isn't enough. Close-up sampling is required. Instruments like mass spectrometer, and SUDA, surface dust analyzer, are designed to collect and analyze particles that Europa might be ejecting into space. By studying the composition of these plume materials, scientists can gain valuable clues about both the surface and what lies beneath the ice. These instruments provide direct chemical analysis to support indirect conclusions about the subsurface ocean and geological processes. Together, these scientific tools give the Europa Clipper an incredibly comprehensive ability to investigate Europa from orbit. In fact, it includes just about every technique possible for a non-landing spacecraft. Unfortunately, this mission won't include a lander. Funding for such a project was cut in 2021, and whether there will be a future lander mission remains uncertain for now. That brings us to the end of the discussion. The Europa Clipper still has over 5 years to go before it reaches Jupiter and begins its operations. What it will ultimately discover remains to be seen. We'll have to be patient and let time reveal the answers. Thank you for sticking with the video all the way to the end, and thanks especially to those who kept requesting updates. Although this time around there weren't any reminder messages, I'm even more grateful to the patrons who continue to support the channel. Oh, and one last thing. The next video about Jupiter is going to be absolutely stunning. Don't forget to subscribe. This is